Hey guys, how's it going? So in this tutorial, I'll be showing you guys how to plot the molecular orbitals of a molecule or a crystal using quantum espresso. So in order to, plot the molecular orbitals such as the highest occupied molecular orbital HOMO, you must have seen these in many research papers and even learned about them in college. So quantum espresso, can be used to plot the molecular orbitals for either the highest or the lowest or any other molecular orbital for that matter. Although in research papers such as this one, you might have seen that people usually provide the HOMO and LUMO of either the crystals and even more popularly for the molecules. So in this tutorial, we'll be using quantum espresso to get the molecular orbitals for benzene and as well as for silicon. So we'll be able to reproduce this paper as well as this paper using quantum espresso. So I think it is a good tool and a skill to have if you're working in the field of GFT, and especially if you're using quantum espresso, because then you can give plots of HOMO LUMO in your research papers and study exciting physics through these. So what we'll be doing is we'll be using the pp.x utility of quantum espresso. So if you Google about it, then you will find out the details about the input file for the pp.x. So essentially it is a post-processing tool, hence the name pp, and it basically consists of two parts in its input. So the first part, that is the ampersand input pp, contains the input regarding what property you want to extract from your system, and the second part basically just plots it and writes it to a file which is suitable for plotting or can be read by external softwares. And one more important thing to note here is that whenever you are going to run pp.x, you first have to run an STF calculation using pw.x, because the results from that will be extracted to calculate the desired quantity, such as the charge density or the molecular orbitals, etc. So in our case, I mean, as you can notice from here, plot num, this particular variable, so you can set it to a number of values, and so as many values you see here, you can do as many things. So in our case, we'll be using 7, which basically gives the contribution of selected wave functions, or in simpler words, it basically gives you psi squared, that is the square of the molecular orbital. And if you are plotting the molecular orbital at gamma point, then you can also specify whether you want the sign of gamma orbital or not, and then you will be able to get positive and negative orbitals. But if you're not using a gamma point, then of course you cannot get a positive and negative part, because there will be a complex, the molecular orbitals will be complex, therefore there will be a real part as well as imaginary part, but you cannot really like combine those and plot them. So you need to square them, and then you only get a positive number, and then you cannot get any sign from it. And but if you are using a gamma point, then you can specify this particular L sign is equal to true, and then you will essentially plot psi square multiplied by the sign of the molecular orbital. But in case of complex molecular orbitals, there is no sign, because there is a positive part then a real part, so it gets complicated, so you just get the psi square. So I guess that is enough information for now. So as you have seen in my past tutorials, I use BRAI to make an input file for silicon, and I use BRAI as well to make the input file for benzene. And the input files look somewhat like this. So for benzene, the input file is pretty simple. We are performing an an SCF calculation, and then I specify the pseudo potential directory, and I told quantum espresso to plot the forces as well as stress, and then I made a large enough unit cell, an orthorhombic unit cell, so that there is at least 10 angstrom or 11 angstrom of vacuum on all three sides, and then the number of atoms is 12 because he's 6H6, and then two types of atoms, occupations are fixed, and one important thing you are noticing here is n band is equal to 16. So why I did that is so that quantum espresso calculates some energy values for the unoccupied orbitals as well, because in order to plot LUMO you will need the information about the unoccupied orbitals or bands in words of condensed matter physics. So I specified the n band is equal to 16. Now how I arrived at that number depends on what pseudo potential you are using. So in my case I was using C.PBERRKJUS and H.PBERRKJUS. So they basically tell me that how many valence electrons are there in this pseudo potential, and that will basically help me to get this value. So for hydrogen, of course, there is a single valence electron, so you get 6 states from hydrogen, but then each electron can, each orbital can accommodate 2 electrons, so you only have like 3 orbitals for hydrogen. And then for C, if we go ahead and try to find this PBERKJUS, so it's in my home directory and inside BURI, cdepot, and C. Okay, C.PBE, I believe. Yep, here. So this one. And then if I open it with a text editor, then if we look over here, then we will notice that it has 2 valence electrons from s orbital and 2 from the p orbital, so a total of 4. So in our case we have 6 carbon atoms, therefore 4 6 are 24, and so 24 and electrons from carbon and 6 electrons from hydrogen. That makes it like 30 total electrons, and since each orbital can accommodate 2 electrons, so we have like 15 occupied orbitals. But we also need to get a LUMO, so we can also specify 1 more orbital to get the LUMO, and you can even make this number even higher, because what happens in some cases is that the orbitals are degenerate. So what this means is, for example, if you look over here for benzene, then you'll notice that this is the LUMO, but there are 2 sets of lowest unoccupied molecular orbitals because they are degenerate. They have the same eigenvalue or eigenenergies, and similarly the HOMOs are degenerate as well. So what we can do is we can increase the number of bands specified, and then we can, we are going to perform only a gamma point calculation, and make sure that you say gamma over here, because then it can take advantages of gamma optimized calculations. And then yeah, pseudo potentials and the coordinates, that's it. So you make sure to add all these input file links in the description down below if you guys have any trouble, but I think this should be pretty straightforward. And then what you're going to do is you're going to run this SCF calculation, which maybe I'll skip for this video because it can take a lot of time. But what we can do is we can run the molecular orbitals plot, because I already have ran the SCF calculation once. So we'll come back to the directory of benzene, and then we will be going to this input file over here. So this is the input file for pp.x, and I'll explain how it helps you to calculate the molecular orbitals. So first you have the input pp name list, in which you will specify the prefix, which should be the same as in your SCF calculation. So here my prefix was SCF, and then you will specify the temporary files directory, which in my case was again temp. So these should be really same. Then fill plot is just a file which will store the data temporarily for use when plotting it. And then plot num is equal to 7 is for molecular orbitals. For other properties you will use another number. And then k point is equal to 1. So in our case we are only performing the calculation at the gamma point. So if you look at the output file, then you'll notice that only energy values for the gamma points are calculated, that is here. So gamma point and then 16 energies. So in our case we are only doing it at the gamma point, so our k point is equal to 1 basically means this. But if you run the calculation for several k points by specifying those explicitly, or even if you give a grid, then Quantum Espresso will list out the k points, then you can give the particular number of the k point in which order they appear to get the orbital for that particular k point. So in our case for gamma we'll use k point is equal to 1, and then k band is equal to 16 basically specifies the which orbital you want. So in our case 16 refers to the first LUMO, and 15 would refer to, I'm sorry, 16, yeah, I was correct, okay, yeah, because they are a total number of 30 electrons. So 16 would refer to the first LUMO, and Then we have the ampersand plot name list, where n file is equal to 1 basically means that here we are, from here we are getting only one file. I think we can even skip this, it will default to 1. And then file pb1 basically means that the first file that, this one again basically means that what we can do is sometimes we can use several of these files. We can calculate several properties at once and then combine them in a linear combination and then plot them at once. So in our case, we'll be only plotting a single file at once. So we have file pp1 is equal to the same as you use in input pb and then the weight. So of course, if there were multiple files that we were trying to plot, then n file will be more than one, and then you will have multiple file pp's, and then you can specify the weights for each of those files. And then output format is equal to 6 refers to that we will get a molecular orbital in a dot cube format, which is a pretty popular format for molecular orbitals, and even Gaussian uses it and is maybe even called the Gaussian cube format. And also it can be easily read by Vesta. So if you guys have watched my Vesta tutorials, and you'll know that Vesta is a really good software. And as you can see here, I just double clicked on the .cube file that I had generated from a previous run, and as you can see over here, it generates a nice little molecular orbital for, it doesn't generate, but it plots them very nicely for benzene. So we'll close that for the moment. And also I'll just go ahead and delete this 16 file so that you can see this calculation happening. Okay, so coming back to the file, yeah, so output format 6 is for .cube. However, there are a variety of other formats as well, but this one is the most convenient for me. And then file out is basically the name of the output file that you'll be plotting or using with external softwares. And then I flag is equal to 3 basically means that you're getting a 3D plot. You can also get 1D and 2D plots for several properties, but for molecular orbitals, it is best represented using a 3D plot. So that's it, but now comes the catch when running the calculation such as this. So here, as you can see, I'm in my benzene directory, but what happens is if I run this pp.x calculation, let me see if I have it in my history, because I am really lazy when it comes to typing. Okay, no. Too bad. Anywho, so we will just type it out once again. Blah 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 blah. Okay, MPI run. It's not necessary to run in parallel, but just and then the address, and that is in the previous directory inside the QE folder, and then inside the bin folder, and then we have the pp.x binary, and then the name of the input file, that is ppmo.in within triangular braces, and then the output file pp .out. So yes, but here comes the catch. When you run this, of course you get an error, and if you open the file, the output file, that is ppmo.out, you'll okay, this is rather weird. Never get this kind of error though. It doesn't work usually, but not this way. I see. The problem is, I think for my last tutorial I showed you how to install Quantum Espresso, and therefore there is no pp.x direct binary right now here. So what we'll have to do is we'll have to compile it. So I'll probably pause the video once again, and also if you guys are interested, then you can watch me compile it. So basically you just go to the Quantum Espresso directory and then give the command make pp. So that should be enough to compile the post-processing utility of the Quantum Espresso, and it will generate a pp.x binary in your bin folder. So let's just wait for it, or maybe I'll just skip it forward, or maybe pause it. Okay, so here it is. So it is now finally compiled. So we'll go back to the benzene directory, and then we will try to run that command once again. So here we'll run the command pp.x, then the input file and the output file, and what you'll notice is now the output file looks something like this. but you will soon notice an error. Yeah, so writing data to file failed due to some weird error, but luckily enough I found a way to circumvent this error. That is, you just avoid giving the input and output files. So you can even give the input in standard output input using the terminal. So you just run the utility, and then it will, it will not prompt you, but it will wait for some input. So what you'll go do is you'll go to the ppmo.in whatever input file, and then just copy the contents of the input pp name list, or you can even type them one by one. So you can even do something like typing input pp or something. But what I'll do is I'll just paste all that and then hit enter, and then we'll calculate this particular property and store it in this file. And then once you see the message writing data to file, then you can go ahead and copy this ampersand plot name list and then paste that as well. So I'll just go ahead and paste that in the terminal and hit enter, and then it will just plot the I forgot to change the name here, so it will be lumo 14 gamma.cube in the output. I should have named it 16. I'm not sure. I think I forgot to rename it. Anywho, so here's the lumo 14 gamma.cube, and if you double click on it, you can open it with Vesta. And you can see here we have a nice little lowest unoccupied molecular orbital for benzene, and if you compare it with the literature, it matches this pi4 molecular orbital. So here it is. Yeah, it matches the pi4 molecular orbital, although not perfectly, but that is the case when you're using different DFT calculations. So this one was done with Gaussian basis sets, while we are using plane wave basis sets, but still, it just goes on to show how powerful quantum espresso can be, even when you're working with molecules. So this is how you can get the plots for molecular orbitals of benzene or any other molecule or nanocluster for that matter. And here's the other LUMO by 5. I'm not sure why I have named all these like weird, like I've named it HOMO for some reason, but it's the LUMO. And then we have, I did these calculations roughly just to check my theories, and here we have the HOMO, which matches this HOMO. Yeah, so I ran some calculations early on just to test it, and yeah, so you can generate the molecular orbitals pretty accurately. And similarly for silicon, I used the input file. So here's the silicon unit cell generated. The input file is generated using BRAI, and it's pretty standard. And then you only just go ahead and specify n band large enough so that it also calculates the molecular orbitals for the energy values for the unoccupied orbitals. And then you will go ahead and run the pp.x utility and specify the k point number as well as the band number, which will specify the molecular orbital essentially. And as you can see over here, here we have HOMO 16 cube, and if you look at it like this, then you'll notice that it matches pretty much this particular HOMO. And here I use the L sign is equal to true, so that I have the positive and negative parts as well. And then I have the LUMO as well, which is, I believe, this now. Yeah, I think I did another calculation using a supercell for that. And here is that particular LUMO at the X point, and in this case you can notice that it's not at the gamma point. So I probably, in my input file I specified something like I created the k points automatically, but then in the output I must have checked to see which of the k points. So in the output they have for this k point, then for this k point, and then for this k point. So there are 2 k points over here, right? So I probably used k point is equal to 2 to get the molecular orbitals corresponding to this k point, and that is basically the X point. So in the pp homo.in I specified k point is equal to 2 and then k band for the HOMO. So that's it. That's how you plot molecular orbitals using quantum espresso. I hope you guys enjoyed this video, and in case you did, then don't forget to hit the like button and subscribe to my channel for more videos like this. Thanks for watching and have a great day.